all of our friends. So today we're going to do a presentation about the key consideration in the selection of ingredients and processing technologies for functional foods and nutraceuticals products. So this presentation will be delivered by Ellen Patiranusadi, Zaki Paralazani, and Shafir Lazrana. Maybe Ellen can continue.
Yeah, thank you, Firly, for I will introduce the presentation. So this is the functional food. There are fortified products, and the example of fortified products is fruit juice fortified with vitamin C, and enriched products, margarine with plant sterile ester, probiotic, prebiotics, altered products, fiber as fat release in meat or ice cream products, enhanced commodities. The example of enhanced commodities is eggs with increased omega-3 on omega-3 content achieved by modifying feed. So this chapter considers the theoretical and technical advancement of some of these processing techniques, and also provide a comprehensive analysis of operational and regulatory challenge faced in their application in food and pharmaceutical industries. So processing technology for functional food, bioactive component, and nutrical products. The processing of nutraceutical can be divided into four steps, namely pretreatment, extraction, isolation, purification, and encapsulation. Pretreatment includes homogenation, grinding, milling, maceration, and drying. All the pretreatment steps, except drying, increase the contact surface area between the extracting solvent and sample containing the desired compound. Drying is an important unit operation that help to increase the shelf life of the raw material. So this is the table of plants, animal, and microbial. You can see allicin, vitamin B, bifidobacterium, bifidum. Maybe next, okay. Solvent extraction. Solvent extraction is the most common method of extraction used for bioactive compound, including phenolics, flavonoids, and edible oils. Different types of solvent extraction method are used, of which the solvent method is the most common and is used as a standard technique for comparison with advanced novel extraction technique. And this is the picture of the solvent. Coolant inlet, condenser, coolant outlet, solvent extractor, and solvent flask. Microwave assisted extraction. Next. Next. Sorry. Microwave energy has been extensively used for extraction of nutraceutical from plant matrix. Application of microwave energy has been shown to increase the extraction yield compared to conventional method. Microwave are electromagnetic wave within the frequency band of 300 until 300. So when a microwave passes through a medium, its energy is absorbed and converted into thermal energy. The conversion of microwave energy into thermal energy occurs via two mechanisms: dipole rotation and ionic conduction. When the radiation frequency corresponds, the rotational motion of the molecule energy transfer takes place, resulting in a homogeneous heating of the solvent. Next. Maybe my friend can continue the presentation.
Okay, so here are the factors affecting microwave extraction. So the performance of microwave affecting extraction process depends on a number of factors. There are solvent choice, microwave power output, extraction temperature, extraction time, and sample characteristic. These operational parameters dictating the efficiency of extraction using MAE are very similar to conventional chocolate extraction. The most important factors affecting microwave extraction are the first one that I said, the solvent choice. So the proper solvent choice provides higher extraction efficiency, which depends on its interaction with the plant matrix and its dielectric properties. The electric properties of the solvent play an important role in defining its ability to extract selected nutraceuticals from plant matrices. So the higher the dielectric constant and the electric loss factor of the solvent, so the higher is the capacity of the solvent to absorb microwave energy and convert it into heat. And it also affects the solubility and selectivity of the analytes into the extraction solvent. Another important factors affecting microwave extraction is addition of salts to the extraction solvent mixture. Increases the heating rate during the MAE process because in addition to the depolarization or ionic conductivity also leads to heat generation in the electric heating. Another important factor is the solvent to sample ratio. So large volumes of solvents are mostly used to increase the extraction recovery, but in the case of MAE, the solvent volume is an important factor, and several studies that have been conducted before have reported that a solvent to sample ratio of 10 to 1 milliliter to 10 to 1 milliliter per milligram to 20 to 1 milliliter per milligram is optimal. And use of higher volume of solvent will also increase the energy and time required to recover the nutraceuticals from the solvent during purification steps. Another factor is extraction temperature. So the dielectric properties of the solvent used for the extraction will govern the extraction temperature. Another factor is the effect of incident microwave power on MAE yield. An increase in microwave power reduces the extraction yield of ascorbic acid due to the damaging high temperature achieved during the extraction process. Another factor is the solvent concentration. So methanol and water influence the extraction yield as the microwave energy absorbing ability of the solvent mixture varied with the proportion of water added to methanol. So this supercritical fluid extraction, or we can call it SFE. Nutraceuticals extracted from natural sources are key elements of the functional food. So several fortified and enriched functional foods contain bioactive compounds extracted from plants and animals. So the SFE technology provides alternative to conventional solvent extraction methods. SFE technique also utilizes the thermodynamic properties of the solvents near the supercritical point. This state is achieved when the solvent's temperature and pressure are raised over its critical value, or we can call it supercritical. Several supercritical fluids, including carbon dioxide, ethane, butane, pentane, water, etc., are used in these SFE processes. Here are some advantages of the supercritical state of the fluid. The first one is the solvating power of the supercritical fluid is higher and can be easily controlled by varying the operating condition of pressure and temperature. Another one is the diffusivity of supercritical fluid is better compared to organic solvents due to lower surface tension and viscosity. Another advantage is application of supercritical fluids leaves minimal to no residue in the final product, and it is non-toxic and it's environmentally friendly. Another one is use of carbon dioxide with appropriate co-solvents such as water or ethanol and methanol enhance the selectivity of the extraction processes. The SFE system works on the principle of distribution of the analyte between two phases, dispersion and stationary phases. During the equilibrium phase between liquid and gas, The partition of the liquid phase increases with an increase in pressure and decreases with an increase in temperature. And if the temperature and pressure are increased simultaneously, the transport properties of both liquid and gas also increases, resulting in convergence. SFE can be considered as a significant alternative to MAE and solid liquid extraction processes. It comes with its own challenge. Several factors have to be considered to develop a successful SFE process, including the first one is the choice of the supercritical fluid. Another one is characteristics and preparation. Another one is the type of co-solvents used to enhance extraction yield. Another significant factors that affect the efficiency of SFE include the temperature and pressure required to generate the supercritical fluid. Any change in operating conditions may lead to decrease in overall efficiency of the SFE process, since the solvating power, diffusivity, and selectivity of the supercritical fluid are governed by changes in the temperature and pressure. For selective extraction using SFE, it is desirable to extract the compound right above the critical point where the targeted compound becomes soluble in the fluid. SFE is one of the environmental cleaner technology that provides higher yields compared to MAE technology and other conventional methods. But the complexity of the design and high operation and its maintenance costs have limited its application to highly marketable products such as decaffeinated coffee, tea, and hops. So this is the supercritical fluid extraction system. So from the carbon dioxide cylinder, it goes to the chiller, and then next it goes to carbon dioxide pump, and it went to extraction vessel, and then back pressure regulator to the collection of the sample. Okay, maybe next Shafirli can continue the explanation. Thank you.
Okay, thank you, Zaki. So I will continue with combined extraction process. Alternative ways to improve the overall efficiency of an extraction process are regularly sought after. One such approach is a combined extraction process, which utilizes the full potential of conventional and novel extraction technologies by employing their core principal advantages to combat each other's disadvantages. For example, the first one, oxide extraction process, is time-consuming, requires high volumes of organic solvents, and has lower yield compared to MAE process. But by combining these two processes, allows engineers to design a continuous process that is easy to scale up or down. Ultrasound-assisted extraction, or UAE, and enzyme-assisted extraction, or EAE. UAE processes could be combined with another novel technique, which is enzyme-assisted extraction, or EAE. EAE is used as an alternative to conventional techniques and is based on the inherent ability of enzymes to function under mild processing conditions and catalyze reactions, as well as their specificity and reduced activity. EAE has been applied for the extraction of bioactive compounds such as carotenoids from marigold flower and tomato skin, polysaccharides from sterculia, and polyphenols with antioxidants pectic polysaccharides from mangosteen. Pulsed electric field, or PEF. PEF can be combined together or used as pre-treatments prior to conventional or novel extraction techniques. PEF's non-thermal applications in inducing increased cell permeability make them an ideal pre-treatment method to enhance mass transfer in food products. PEF could be a good alternative to conventional pre-treatment methods of homogenization, grinding, milling, maceration, and drying because it offers higher yield and quality, but practical implementation on an industrial scale is very limited because of the complexity in the design of the treatment chambers that are used to process high volumes of raw materials. The application of high electric field could also be a safety concern for workers. Next is delivery of nutraceuticals in food and its limitations. The measures of the effectiveness of nutraceuticals added in food is related to their bioavailability and bioactivity. Nutraceuticals are stable when processed under certain conditions like controlled temperature, pressure, oxidation, and light, employed during the processing of food. However, the environmental condition like pH, presence of enzymes, and other nutrients within the gut can significantly affect their bioavailability. Nutraceuticals and function food components come in different forms and are unique in their molecular structure, polarity, and molecular weight. These differences confer varied physiochemical properties, including solubility, partitioning, and chemical and optical stability. The design of the delivery system depends on the physiochemical properties of the nutraceuticals and functional food components. Bioactive lipids, including carotenoids, conjugated linoleic acid or CLA, omega-3 fatty acids, and phytosterols are difficult to deliver because of the following challenges. The first one is bioactive lipids have low water solubility. Hence, they have to be encapsulated within delivery systems such as emulsion or microemulsions to make them dispersible in aqueous food products. Next is carotenoids exist in a crystalline form at room temperature, and hence their delivery requires elevated temperature, or they may influence the organoleptic quality and shelf life stability of the food products. And last one is the majority of bioactive lipids, such as omega-3 fatty acids, carotene, and lycopene, are thermolabile and photosensitive, and hence they have to be kept within a protective delivery. Some of the delivery systems that are currently used or could be used to deliver bioactive compounds by the food industries are the following. The first one is lipid-based nano-structured delivery systems, which consist of one or two lipid bilayers fabricated from food-grade phospholipids derived from sources such as soy, dairy, or egg. They are suitable for the delivery of hydrophobic nutraceuticals compounds. Next is emulsion. Multiple emulsions provide the ability to deliver two or more nutraceuticals products that can adversely interact with each other. Next is micelles and microemulsions. Oil and water emulsions with a particle size below 50 nanometers are thermodynamically stable and have high optical clarity. The only disadvantages they have is that the surfactants used to make them are usually not food grade and can be dangerous or injurious to health. Next is biopolymer-based delivery systems or proteins and polysaccharides. The main advantage of these systems is that they provide the required thermodynamic stability but have low loading capacity and often affect the organoleptic and physiochemical properties of the food. So in conclusion, functional foods and nutraceuticals are a growing market. The design of suitable processing and delivery systems for nutraceuticals and functional food components of interest is still a growing field. Extensive research will continue to be required to develop effective delivery systems and new functional food and nutraceuticals products. Additionally, regulatory reforms may be required to allow manufacturers to produce, introduce, and market novel functional food and nutraceuticals products. So that's all from our presentation. Thank you.